I guess it's kind of all or nothing, isn't it? Yeah, okay.
Is it better this way?
Better for napping. Yeah, okay.
See, let me get my iced tea here so I can function.
Good morning. So I'm Colin Ressler, and I am in the Department of Earth and Oceanographic Science at Bowdoin College, which is a small liberal arts college just about 40 minutes from here down, about 2 peninsulas away. So I will be talking today in an overview lecture, very similar to what Kurt was talking about, but also giving you a little bit of detail on the breadth of the topics that you guys will be learning about in the next few weeks. So I wanted to just start with this. I love this image for just so many reasons. But what I love is that everything that you see in this image we will actually be talking about in the class. We'll be talking about how light penetrates into the ocean and looking at how the changes in intensity vary as a function of angle and a function of depth. And you can see some color variations in there too. And so it's when you look at the PDF, you'll see a nicer version than is actually appearing on the screen. So I wanted to start with this this figure from Kurt's book, and he already talked about this, where he partitions all of the various properties, optical properties, and the first ones that we'll be talking about this week are the inherent optical properties, absorption and scattering, and attenuation. And those are measured properties, and we'll be measuring those properties in lab this week. The other set of properties that you can measure are the radiometric properties, and we'll be measuring those next week. And those are the radiance and irradiance that Kurt just talked about. And if you think about the properties of light that you're measuring in the ocean, they vary quite a bit. They vary with wavelength, they vary with depth, they vary with angle. And they're dependent upon the optical properties of the water. And so the constituents in the water have absorption and scattering properties, and those absorption and scattering change the way light propagates through the ocean. And we describe that in a forward sense with the radiative transfer equation. And that process, which allows you to measure the properties of the constituents of the ocean and then predict what the light field looks like in a forward sense via the radiative transfer equation, is what hydrolight does. And so you'll be spending some weeks on hydrolight where you input optical properties that you've measured in the lab or in the field and predict what the radiometric properties of the ocean are. And then, of course, you can compare it to the radiometric properties that you would measure with various radiometers. The other thing that we can do with the radiometric properties is actually compute what we call apparent optical properties. These properties are derived from light measurements, but they provide us with descriptions of the optical properties of the water. Again, now they're not inherent to the water, but they're related. And so we'll also talk about how we can take apparent optical properties derived from light measurements and actually predict the inherent optical properties or absorption and scattering. And that is basically the entire course. Okay. So today I wanted to start with thinking about the light coming from the sun and entering into the ocean, just to make sure that everybody's on the same page as we start to really delve into some detail that we'll get into till tomorrow. So I want to talk about the source. So the source, of course, is the sun, right? And so my question to you is, what's the intensity and the color of the sun? Any ideas? Okay, you might not know the intensity of the sun. So there's a solar constant. But do you know the color of the sun? What? What color is it? White. White. How do you know that? You looked at the sun?
No.
Correct. The answer is no. You did not look at the sun, because you shouldn't look at the sun because you'll burn your eyes. But in fact, we've all looked at the sun, right? Yeah. And it's white. right? So if you look, and particularly if you were in the space station, I just think this is an awesome image. This is taken from the space station, and you can see the sun in the sky, in the space, and it is indeed quite white, which means, of course, that it's got approximately equal energy in all wavelengths, and that's why it appears white. Don't look at the sun. Okay, measure it. We have sensors to measure it. Don't look at it with your eyes. Okay, so we know that the sun can be approximated as a black body. And so when we think about black body radiation, we have to think about the fact that any object that has a temperature greater than 0 Kelvin is going to emit some electromagnetic radiation. And the sun emits a lot of electromagnetic radiation, and so do you. Each of you emit electromagnetic radiation. So Planck's law, or Planck's law, it's Planck, right? Planck, describes the spectrum of energy that is emitted by that body as a function of its temperature. And it's very complex, and this is the equation here. This is the brightness at some wavelength as, for a body of a certain temperature, and you recognize some of the constants in here: Planck's constant, Boltzmann's constant, temperature, and wavelength. And this is a graph of what it looks like. So, for example, the sun is about 5,700 degrees. We could say 6,000 degrees. And so this is the spectrum of energy that it's emitting, right? And most of the energy that the sun emits is in the visible because of its temperature. If it were hotter, it would emit more ultraviolet radiation. And if it were cooler, it would emit more infrared radiation. A lot less overall radiation, but also shifted spectrally. And so you've probably done exercises like this where you've looked at the spectrum of what the Earth emits based upon its temperature. It emits mostly in the infrared. So what do you think you emit? Infrared. But you'll also notice that there's a tail that comes off of here too. So it turns out you also emit microwave. So I used to work with some microwave scientists, and they had little handheld microwave radiometers, and they would just come up and hold it next to you and be like, "Yep, you're emitting microwave. Dangerous." So, but it wasn't, of course, because you're a very low emitter. But the point being that as you change the temperature, you change the spectrum of energy that's emitted. So I have my undergraduates in one of my classes actually program up Planck's equation here, and so you can put in all the different values, and you can plot it out, and it's just a good exercise in introduction to MATLAB and how you can put equations into MATLAB and then how you graph them. So that's lab 1. And so they predict the black body radiation using Planck's equation for the sun, and we scale it to what it would be at the surface of the Earth. And so if we just blow up the visible part of the spectrum here, we get a spectrum that looks something like this. And this is the energy flux as a function of wavelength. And of course, what you see is that the Planck's equation predicts that the sun is white, right? Mostly equal amounts of energy at each wavelength. So I also take them out and have them measure the spectrum of light. And so here was a spectrum of solar radiation that was measured. This was calculated for our latitude, time of day, and time of year. And so what can you tell me about the modeled versus the measured solar spectrum? There's definitely some influence between what you would predict versus what you measure. And of course, we're going through the atmosphere. And so there's an overall reduction, and then there's also features, right? Okay, so it's Earth's atmosphere. This is another one of my favorite images. So this is showing the sunrise coming up over from the Earth. Again, it's from the space station. And so talk to me about the atmosphere. What's it look like? What are some things that you notice about this image? What? It's blue. Yes, the atmosphere looks blue, particularly here. What else?
There's 2 layers?
It looks like there's 2 layers. So there's this very whitish layer and then this bluish layer, but there's actually, it's even purple right here if you come up close. So there's a gradation in the properties of the atmosphere. This one is much more white, and this one's much more blue. And so you can see that there's something, if the source of light is coming from the sun, but we're seeing light way over here, why are we seeing light way over here? Yeah, scattering. So there's a lot of particles in the atmosphere that are scattering. And it turns out that if you see the color, it's scattering light of different wavelengths. We'll talk a lot about how scattering is dependent upon the size of the particles. And so we can see that very clearly in this image of the atmosphere. Okay, so here is a spectrum of the solar spectrum at the top of the atmosphere. Here's what it is at the surface of the Earth. So this is what you lose going through the atmosphere. And here we are at 10 meters below the ocean surface. And so we're losing a lot of radiation in the atmosphere, mostly due to the absorption by atmospheric gases. And in the visible, we're mostly concerned, well, UV mostly is ozone. But in the visible, it's mostly oxygen and water vapor in the atmosphere that's taking out this overall energy here in these bands. Once we get below the surface, what are we losing in terms of colors of light? Red, right? And of course, we all know why that is. Do we all know why that is? Maybe not yet. Longer wavelengths are being absorbed by water very efficiently. And so the ocean looks black in the infrared because no light is able to get out. It's all being absorbed. And then we can look at little features in here, and although it's not the point of this graph, what you'll see is that as we start to lose various wavelengths in here, we can relate that to the particulate and dissolved constituents in the water. And that's something that we'll be doing in week 3. Okay, so in the absence of an atmosphere, the color of the sun is white, right? What's the color of the sky in the absence of an atmosphere? Yeah, what'd you say? White? So that would mean that if there was just the sun and there was no atmosphere on Earth, we would see a white sky. Yeah? Black. Okay, so we have black and white. Okay, so black would mean there's no light coming from the sky, and white would mean there's all sorts of light coming from the sky. Which is it? Well, let's think about it. If there's no atmosphere, there's no gases absorbing, there's no particle scattering. And so if we look at the sun, we see white. If we look away from the sun, we see black. We see space. Because the sky looks bright because the atmosphere is scattering light from the sun into the atmosphere. Does everyone see me there? So it would look like the sky looks from the space station. If you go back to my second slide, the sky is black. Okay? So the atmosphere is what gives us the blue sky. In the absence of the atmosphere, the sky would be black and there'd be a solar beam. Now, why am I asking you this? Because there's a lot of models that were based upon predictions of a solar beam striking the Earth and modeling of that solar beam. And they ignored skylight. And so you have to, in your mind, ignore the fact that there's photons coming from the sky which happen to be blue and which are coming at a different angle than the beam of light coming from the sun. So when you read papers, make sure you check to see what their assumptions are, because we know very well that there's plenty of skylight. And we're actually going to have you measure the total irradiance and then the irradiance of the sky in the absence of the sun. And it's a different spectrum. And it's a different intensity. And it's a different radiance distribution. And those all become important when you make your measurements, if you make your measurements at noon, you're dominated by the sun. If you make your measurements of of sunlight in the afternoon when the sun's way over here, most of the light you're measuring is skylight. And it's a different color than the sun. Okay, so, and if we had no atmosphere, the sky would be black. And the angular distribution of the light incident on the Earth in the absence of an atmosphere is determined solely by the sun. So whatever the direction of sunlight is, that would be the directionality of the incident light. Okay? And the sun is so far away that by the time its beams of light get here, they're parallel. So you can just look at the direction of the sun, and that's the angular distribution of your incident light. In the absence of the atmosphere. As soon as we put the atmosphere in, now the color of the sun is it depends on what's in the atmosphere. Because you could be absorbing some wavelengths away from the solar beam. You are also scattering preferentially certain wavelengths away from the sun. So the sun can start to look a little bit more yellow, which I personally haven't looked at it in a long time, but it looks a little bit yellow, okay? And the color of the sky, of course, if it's clear, it's blue. If it's cloudy, it's white, based upon the scattering properties of the atmosphere. And the angular distribution of the light with an atmosphere. It comes from everywhere, right? So most of it will probably come from the sun, but you've got a lot of light coming in at different angles from skylight. And if you have clouds, you can have a very diffuse light. And Kurt will talk a lot about the distribution of light coming from the sky incident on the ocean. And you need to know what that is if you're going to have any hope of doing a good job modeling the light field in the ocean. You need to know what that distribution is incident on the ocean, okay? Okay, so in general, the atmosphere reduces the intensity, changes the color, and changes the angular distribution. And so there's a whole field looking at radiative transfer in the atmosphere based upon the optical properties of the atmosphere, its absorption and scattering. Okay. All right, so we're going to have you consider what natural variations are in the solar spectrum. You'll be able to make a bunch of measurements of that. And think about how that spectrum changes with latitude, time of day, state of the atmosphere. But then we also want you to think a little bit about measurement-induced variations in the solar spectrum, depending upon which type of a sensor you're using, how you're deploying it, et cetera. So you'll be able to distinguish what's nature versus what's measurement. So we'll spend some time on that, I think, next week or third week. And we'll have you try for yourself looking at these natural variations in skylight and the sun. Okay, so the impacts of clouds. Well, certainly clouds change the intensity, right? They can absorb, they can also scatter. And so it depends on if you're measuring radiance to a bright part of the sun or a bright part because of the clouds. They change the color. They change the distribution in terms of the angular distribution. And they certainly have a huge impact on remote sensing, which Jeremy will talk about in a couple of weeks. So there's a funny cartoon called Calvin and Hobbes. How many people have heard of Calvin and Hobbes? Okay, it's an American cartoon from, probably 25 years ago. But anyway, Calvin's kind of a brat. And he's definitely always testing his dad. So he's like, hey, Dad, what are clouds made of? I used to know that. I think they're mostly water. So how come they float? Well, it's sort of evaporated water. And maybe there's some other gases in there, too. I'm not too sure. So why are they white when the rest of the sky is blue? Says 6-year-old Calvin. Well, heck, beats me. I guess we should look this stuff up. Oh, I take it there's not a qualifying exam to be a dad. I imagine there's a number of you who've already taken your qualifying exam. So you should be able to answer all of these questions: what clouds are made of, how come they float, and why are they white when the rest of the sky is blue. And if you don't know that by the end of this class, we'll chat, because you want to pass your qualifying exam. Okay, so we've taken the energy from the sun, we've brought it through the atmosphere, and now we're at the ocean's surface. And so I wanted to show this image. Oh, this is not showing my whole screen. Manuel, how do I do this? Because it's cutting off my screen. I guess I'll just read it. Okay. So this is an atoll in the Indian Ocean. And this strange patterns, this is taken from satellite, is due solely to surface processes. So you have changes in the reflection of light off of the ocean and off of this atoll, which give you this very spooky image, because it doesn't look like the ocean at all, does it? But you have all this glitter here reflecting off the surface. You've got probably very intense green-blue water in here, but also specular reflection off of here. And so imagine now you get this data from satellite, and someone says, we need to know how much chlorophyll's in the water. That's going to be a tough one to figure out because of all of these surface effects. So we'll talk about surface effects on remote sensing and what happens when light interacts with the surface. Part of it goes into the water, some of it comes out of the water, maybe nicely here, but this is pure reflection off of the interface. So, okay, so now we allow light to go into the surface and it propagates to depth. So what happens to the light as it's going through the ocean? I already know the answer, so you have to answer. Yeah. It can be absorbed. I always start with absorption too. What else?
Yes.
It can be scattered. Yep. What else? Huh? It could be in the water. When we think of something like as being reflected, you could think of it being reflecting off of a particle or something, but that would be scattering. Yeah. Anything else can happen to it? Huh? It can be used by phytoplankton. So they absorb light and they use that for photosynthesis, or it can go into heat. And what else do they do? They can fluoresce, right? So there can be re-emission. It could be Raman emission. It can be fluorescence. But those are the processes that are going to impact light as it goes through the ocean. And hydrolight has ways of dealing with each one of these individually in terms of particularly the re-emission is something that we'll spend some time on. Okay, so I want to consider some case studies. And the first case study I want you to think about is an ocean that doesn't have any particles, okay, but does have absorption. And so when you look at this ocean, what's it going to look like? Transparent but colored. So why transparent? Because there's no particles, right? So if you're diving and you're on your back and you're going down, what are you going to see as you go deeper and deeper? The same scene. What will the brightness of light look like? It will diminish. Why? Because of absorption. Because that ocean absorbs. So as you go deeper, it's going to get darker and darker and darker, and you will get to a point when all the light is gone, right? Now get yourself back in the boat and look down at your ocean. What does it look like? Why blue?
Reflecting the blue wave radiation.
That is true for the open ocean. But I've given you an ocean that absorbs all wavelengths. You are right on track for the actual ocean. I'm giving you an ocean that has no particles and does have absorption. Imagine it all wavelengths equally.
No scattering, only absorption.
Yes.
Deep ocean, it will look dark.
The deep ocean will look dark, and the surface looking down on it will will be black because there are no particles to redirect the light back out to your eye. All of the light continues to propagate down until it's absorbed. So as you go down, it will get darker and darker and darker and darker. And as you look at it from the top, it will be black. So when we look at the ocean and we see light coming out of the ocean, that tells us one thing. We have particles. Or something is scattering light back out the surface. If there were no particles, the ocean would look black. Okay? Anyone not with me on this? Now, if the spectrum of the absorption, say, was bigger in the red than in the blue, as you went deeper and deeper, you might lose red light first, and it would get bluer and bluer and bluer until it got black at the bottom. You still would not see blue light coming out the top because it's never redirected by scattering. You would only be able to detect that as you were diving down, and you would lose different colors. Okay? So, do we have a natural analog that we could point to? What kind of things would you look for in a water body to replicate this high absorption, no scattering? Well, we know water absorbs, right? Water absorbs red light very strongly. What absorbs blue light? Does anyone know yet? What'd you say? You said phytoplankton, right? Yes, they do. They do absorb, but they also scatter, so we have to rule them out. Sedum. Sedum, colored, dissolved, organic matter. Dissolved, doesn't scatter, but absorbs blue light really efficiently. And so, in fact, that is a good analog. And this is an image. It's a false color image, but I'm going to show you a real image. But this is the Rio Negro. And this is the Amazon River coming in down here. I think it's the Solomos. I don't know how to pronounce that. But this is a regular sort of typical optical property river. But you can see how the joining of this very black river with this typical blue river right here. And the reason why this one is so black is because it has so much sedum in it. And in fact, this is the joining of those two. And here's the line where those two join. And so this one, you can say a couple of things about these two rivers. What can you say about this one? Lots of sediment, lots of particles, lots of scattering. Also probably has quite a bit of sedum because the color that you see is sort of brownish, right? And what can you say about this one? That's a lot of sedum and probably no particles. Right? So just by looking at this now, you immediately have an intuition about what's in the water, just by looking at the color, the brightness, and the intensity of the light coming out. Right? If you get closer, this is what the water looks like. This is the blow up. This is along the shore. But this is what the water looks like. That's a lot of sedum. Right? So light doesn't penetrate very deep. Okay, so that's one case study. All right, now consider an ocean that doesn't have absorption, but does have particles. Okay. So, as I look down on this ocean, what's it going to look like? James, do you have a... It's James, right? Yeah. It will what? So, has no absorption. So you have to pretend that the water doesn't absorb. There's no absorption. But it's not going to be blue because it's blue. You're thinking blue because water absorbs red, but just forget it. This is a hypothetical ocean. It doesn't have absorption. This is what makes these problems so difficult, right?
You're gonna see the bottom of the ocean, but totally blue because there is a lot of scattering.
Why blue?
I didn't say blue.
You did say blue. Did he say blue?
Blue, like with kind of a not really not clear.
Not clear.
Is it because the blue travels farther than red?
Blue travels farther than red because water absorbs red. But I've told you to ignore the absorption by water.
So it would be a rainbow color.
What's rainbow colored? When you add the rainbow together, what is it? What? It's white.
It also depends on how large the particle is.
Oh, yes, some particles will scatter light preferentially, but by the time you see the light coming out, right? Yeah, so, and let's just say it's big particles. And so they're going to scatter light equally at all wavelengths. And so the ocean will look white. And as you travel down, does it get darker? Nope. So if we had an ocean with no absorption and just particles, it would be lit down to 5,000 meters. Wouldn't that be awesome? Yeah. Okay, we don't have that. But anyway, you can think of ice as being sort of an analogy of that, where, so here's the water that looks really dark because we have strong absorption, and here's the water in its frozen form, but its scattering properties dominate, and so it's basically white, and here's the icebreaker going through these ice flows. So that might be an analogy. Another one you might think about is a coccolithophore bloom. So we'll learn about coccolithophores. They're phytoplankton, but they have these really interesting calcareous tests on the outside that scatter white light. And this is a bloom off of, in the English Channel, and there's some colors to it, but you can see just how much brighter it is compared to the surrounding ocean. And that's because it's dominated by the scattering properties of the particles rather than the absorption properties. Okay, so we have a somewhat natural analog. So these are really hypothetical, unrealistic, mostly examples. But I think what's important, we were talking about white light, but when you think about the ocean and you think about it in certain narrow wave bands, you can actually go to these case study or extremes. So you might find a wave band where the ocean does behave as a pure absorber, where scattering doesn't really play a role, or where the absorption is so small that it appears white in that waveband or very bright. Okay, so you can think about the ocean looks like a pure absorber in the infrared because water absorption is so strong that we don't get any infrared light back out, and so it looks black in the infrared. And we begin to use that when we think of remote sensing. Sometimes we pick those wavelengths on purpose because then we know that the ocean isn't actually emitting any light. And that becomes a very useful tool for us. Similarly, you can think of it as you get into in clear ocean waters, you can think about absorption being very, very low in the blue because the only thing that's really in the water is water, and water has a very low absorption coefficient in the blue. And so all the light that you see can be attributed to dominance by scattering in the blue. And so you can begin to play some interesting theoretical games by going to certain wave bands and making these approximations. And that can help you think about sort of understanding if your data are good, understanding if your models are predictive, by picking these wave bands and recognizing that you can take it to these extremes. Okay? All right. So this was not the image that Ivana sent the other day, which I'm going to leave to her because I think maybe she'll show it sometime. It's the image that just came from NASA, the one, yeah, which is so spectacular, but I wanted to leave it for you. You can show it in one of your lectures. It's just like one of the most beautiful NASA images ever, but this one is pretty spectacular. Huh?
I have a nail sticker of that image, and I can hook you up with that one.
That would be awesome. So this is a MODIS image of a phytoplankton bloom in the Barents Sea. And hopefully you can see it on the screen. You'll be able to see it in the PowerPoint. But just the incredible array of colors and brightness and features. And to be able to look at this image and say something about the underlying ecology is really what we try to do based upon the color and the brightness. You can tell the concentration, you might be able to tell the depth, you might be able to tell the size of the particles. And so you have this infinite combination of absorption and scattering, which gives rise to this beautiful emanation of light out the surface. And so that's really what we try to do in an inverse sense, is by measuring the light, trying to infer what's in the water. Okay. So now I want to get into a little bit more in detail about the processes of absorption and scattering in the ocean. And so what I encourage you to do, if you do not already do this, is every time you go out to the ocean, look at it. And look at its color. And look at its brightness. And see how turbid it is. And then you collect your water samples and you measure chlorophyll, you measure particles, you measure all these optical properties, but begin to tie your observations of the color and clarity and brightness of the ocean to the optical properties and the biogeochemical properties that you're measuring. And you will start to become very intuitive. You'll be able to look at the water and say, 2.5 micrograms per liter chlorophyll. Or, wow, a lot of CDOM. Or, wow, there's no particles in the water. That green is caused by CDOM and not by phytoplankton. So begin to develop sort of this internal library for yourself. It's like a lookup table, but you can develop it for yourself. So that becomes your clue for interpreting color, interpreting clarity, and interpreting brightness. And that will help. Okay, so I want to talk about beam attenuation. And Emmanuel's going to spend more time talking about beam attenuation. But I want to just start by saying we have absorption, which we call A. We have scattering, which we call B. And we have beam attenuation, which we call C, for no apparent reason, except that A plus B equals C. And I'm not sure if that's where it came from, but I wouldn't be surprised. Kurt, any comments?
Well, in the old days, A was
Alpha.
A was A, B was sigma, and C was alpha for attenuation.
Right. And that was really nasty.
With Morel, Preisendorf, Ray Smith, et cetera, and they had like big fist fights and whatever over the proper notation. And they ended up with A plus B equals C instead of A plus sigma equals alpha. And that's
Because that was mixing alphabets and, yeah. This is so much easier. And so the beam attenuation, some people call it beam C. It's somewhat related to transmission. I'll show you how. Not to be confused with diffuse attenuation, which is an apparent optical property. But anyway, so IOPs, inherent optical properties, are primarily determined by the concentration and composition of the particulate and dissolved substances in the medium and water itself. It's independent of the light field. And people always say, what do you mean by that? And what I mean by that is when we measure them, we block out the sunlight. If you're trying to measure the IOPs, you don't want the sun anywhere in your measurements because you're providing a light source and you don't want the sun to be contaminating your signal. And you can measure IOPs with an instrument in the water, or you can take the water out of the ocean and bring it into your lab and measure the exact same optical property as you measured in the ocean. Because the property that you're measuring is inherent to the water and has nothing to do with where that water is, as long as you haven't changed the water in the process of putting it in the lab. Okay, so has anyone ever heard of Clark Little before? He's the wave photograph guy. He's totally awesome, right? Okay. So there he is with his camera, shining a picture at that wave. And then here he is with his camera shining a picture of that wave. So what can you tell me about those two different oceans, those two different ocean waves, aside from the cool waviness about them? In terms of their optical properties of the water, is there anything you can say off the bat?
Much more chlorophyll in the green.
There is something making this water green. And it could be chlorophyll, which is absorbing the blue light, or it could be CDOM, but something is absorbing blue light compared to this, which is very, very blue in color. Okay, so we already can see that there's something different. Okay, what about this one? Oh, I know. This is just so amazing. I'm sorry, I'm blocking you. So amazingly beautiful. What do we see in that wave? A lot of sediment, right? So we can immediately talk about the gradients and particle scattering by just looking at how the color and the turbidity and the brightness compares to looking through this layer of very clear water. Okay, that was just for fun. Okay, so now we have to do the hard part, which is before we actually are going to measure the IOPs, we need to review what they are so that we know that we're measuring them correctly. So imagine you have an infinitesimally thin layer of material, it can be water, and you have some incident radiant power incident on that layer, on that face. And you have some transmitted radiant power coming out. And say there's no attenuation, there's no absorption or scattering. What can you tell me about this versus this? They will be the same, yes. Okay. Now, if the transmitted is less than the incident, then you say you have attenuation. And you've lost some fraction of the power through that layer. And if you had lost it due to absorption, we can call this the absorbed radiant power. That's the amount that you lost due to the process of absorption. If instead some of that radiant power was redirected due to scattering, we haven't lost it, we've just redirected it. We can call that scattered. Ooh, that should be power. I moved from flux to power. And I did it here too. So these should all be power. Sorry, I was switching out my overheads. So you could also have loss, the loss from the transmission due to absorption and scattering, and of course that would be total attenuation. So we know from conservation that the incident has to equal the sum of what got transmitted plus what got absorbed plus what got scattered. And this is the basis of spectrophotometry, is just looking at where that flux of power ends up. So we can define something called attenuance. We're not going to do it for very long because there's a lot of terminology, but we'll just call attenuance. It's a capital C. It's the fraction of that incident power that got attenuated. And so we can see that is equal to the scattered plus absorbed divided by the incident. And that, of course, is equal to what was incident minus the transmitted, because that's the difference from what was transmitted, right? And we can then define the beam attenuation coefficient as being the attenuance per path length. And so the path length is the thickness of your layer. Now, in a perfect instrument, we could squeeze that down to its limit. And as that layer goes to 0, we can look at the limit of this change in power over the incident power. And so, of course, anytime we see a limit, that makes us think of what? It makes us think of integration. And so we're going to integrate this as the integral of the attenuation coefficient over this path length and the differential power over the total power. So what's 1 over phi d phi? Does anyone remember that? What that integral is? I always look it up. But I looked it up before I came. What? Did you have an idea? It's log. Very good. So when we integrate this, of course, the integral of c dx is cx, evaluated from 0 to x. And this is the natural log of phi integrated from the incident on one side of the layer to what the phi is on the other side of the layer. Well, what is this term going to be? If you're evaluating Cx, where x goes from 0 to x. X squared. Oh, we've already integrated. So now we're just evaluating.
Oh, sorry. So versus when it would just be
Yeah. So it's just going to be Cx, right? Because it's C times X minus C times 0, so that'll just be Cx. Now we're going to evaluate this. Well, what is phi on, when X is 0, we're on this side. So what is phi on this side of the plane? Yep, it's the incident. And what is it on this side of the plane? The transmitted, right. So we just have this, okay? Well, the cool thing about logs are that when you have the difference of the log, it's the same as dividing. Yep. So let's see. Oh, I evaluated. There I go. And so it's the same thing as the natural log of the transmitted over the incident. All right? So if we're solving for C, the beam attenuation, which has units of per meter, because this ratio's out, it's units, and this has units of per meter, we're looking at the loss of power over this path length. And so if we want to build a sensor to measure this, what do we need to know? What is this? The path. We need to know the path that the photons are traveling, which may or may not be the geometric path, depending upon the instrument. But we need to figure out what that path length is. If it's a absorption meter, it might be 25 centimeters. If it's a spectrophotometer, it might be the width of your cuvette. If it's a filter pad that you've measured absorption on, you'll learn how to do that. You have to figure out what the path length is that the photons would travel through. So when you're building a sensor or when you're using a sensor, you need to know what X is. Okay? And then what else do we need to measure? We need to know how much light is incident and how much light is transmitted. And our ability to determine the beam attenuation hinges on knowing what the intensity of the incident light is and whether it varies, and it will, and measuring how much is transmitted. And how we detect how it's transmitted matters a lot. It matters whether we're measuring the irradiance, which is coming through onto a cosine type of sensor, whether its radiance is a solid angle and we're measuring its some distinct angle. It matters how you detect transmitted radiation. And so as we begin to work with instruments that measure beam attenuation, i.e. transmissometers, which probably is one of the first optical sensors developed, it makes a huge difference what its path length is, how you measure the transmitted radiance, and how you keep track of what the incident irradiance is. And so your uncertainty in this measurement, and I think Emmanuel's going to talk an awful lot about this, depends upon the sensor and how well you've characterized all these different properties of that sensor. Okay? Any questions on that? Okay. So, that's what I just said. Okay, lab 2. Okay, so we can go through the same argument and derive this for absorption. And so we derive absorption from absorbance per path. We integrate, oh, I'm sorry, that was just phi over, since we don't have any scattering, we're just looking at the loss due to absorbance. And we get the same exact equation for absorption. The same exact equation, well, that's cool because we need to know the path length, we need to know the transmitted radiation, we need to know the incident radiance. So how can we get a beam attenuation and absorption from the same sensor? They have exactly the same equation. How can that be? Why do we have absorption meters and beam attenuation meters? They're different, right? How many people have worked with an AC9 or an ACS? Has anyone worked with one? See a couple of hands in there. We have two different modes of measurement. One gives us absorption, one gives us attenuation, but they have the exact same equation. How can that possibly be? They're very different measurements.
Because in one, the tube through which the water is passing, there is a mirror inside, and the other one is black.
Mm-hmm.
So
And what does that mean? So he's
that
saying,
mean one,
yeah, go ahead.
that means one's gonna absorb all the photons when they are like scattering, whereas the other one is gonna like keep being inside and go to the end.
If you have your incident flux and you have your transmitted, and here's your sample, if light goes in here and maybe gets absorbed so it's a little bit less coming out, when you measure the transmission, you are measuring the loss due to absorption. But what if the particle is scattered? The particle scatters the light out of the detector. Then what you've measured is attenuation because you're looking at the loss due to absorption and scattering. But if you cleverly did something here to make this scatter back into your detector, then you've captured your scattered light and your transmission loss is due solely to absorption. So changing whether the scattering is lost versus scattering is captured allows you to make virtually the identical instrument with the same path length, the same intensity beam, and the same detected beam, but you're able to measure two different things. Because in one configuration you've excluded scattering, and in the other configuration you've included it. Okay? So you have to think very carefully about this term and what that term includes. And we'll talk about that when we talk about AC meters. Okay? All right. That's how it's different from beam C. Okay, is it 12 or is it 5 to 12? It's 12. Okay, so what did you want to do?
Have lunch and come back.
Okay, that sounds good.
The crew at the kitchen really likes it.
Yes. So this is what happens when we started. We started half an hour late, I think, so we're a little bit. But I think we're okay.